Welcome back. In the last clip we prepared the collision of our boat, so now we are starting with the high-res ocean simulation. First, let's dive into our guided ocean layer initial once more and adjust the size of our simulation area, because it's not necessary to simulate so much space to the left and to the right. So let's adjust these values here. For the X, I think a 41 is fine. You will immediately see how it will decrease here. And the height also a 15, and for the Z-axis let's put a 21. Okay, so now we have to simulate less particles, which will speed up our simulation. But one more thing we're going to adjust is that at the moment the thickness here of our ocean, it's pretty thin. So let's see here, the layer size parameter will define how deep our ocean is. So in many cases this default value is fine, because if you have a deeper ocean you also have to simulate more particles. But in our case the waves are so high and our boat will dive in so deep when it comes down from a wave crest here, and it will smash into the water, so we need to increase the layer size here a bit. So we don't have to break the connection, just put instead of the 8 a 16 here, and you will see that now we will have a thicker layer here. Just display it, and yeah, now it's thicker. That's what we're looking for. And also we can just move it down a bit, just put a 2.5 here. Okay, so we have enough space down here. That's fine. So we are nearly ready for the first simulation. As mentioned in the last clip, if you have less than 16 GB of memory in your machine, I would recommend caching this wave tank out here before feeding it into the simulation. Okay, so here's our boat. Let's just display not the modified version here. That's fine. And jump back up and into our guided ocean layer sim. To do some more tests, just increase the particle separation again to iterate faster. Okay, that's better. Let's jump to frame 3 here to see how fast it goes. That's pretty fine. A good speed to iterate, and you can see our collisions are also looking pretty nice, but for now just hide them. And let's display our boat geometry. To do flipbooks with different values, I would recommend dropping down a camera into your scene. Let's do it. Drop it down and move it to a proper position, just to have a good overview. And if you do flipbooks, you will always do it from the same position, so you can wipe between two different settings and you will see the difference pretty easy. Okay, that's fine. And let's jump into our simulation here. If we take a closer look here on the flip solver, there are several values for the particle motion and the volume motion especially. So some of these values here are not interesting for us, like viscosity for example, because our fluid here is normal water, and the presets which are on the flip solver here, if you use the ocean shelves, they are already set up for water. So we will do some adjustments, but we won't step through every parameter here. One more thing I would recommend to find good values is to have a good overview. So if, for example, if you do a flipbook, one more, you will always change a parameter, the collision separation for example, or you will increase the collision velocity. Sometimes it's a bit difficult to keep track of all the changes you make. Perhaps in the end you have 20 flipbooks there, and then you will see that perhaps in flipbook 12 the collision is fine, in flipbook 16 the wave height is fine. So somehow we need to keep track of our changes, and there comes a really handy feature here that we can add parameters on our camera, and these parameters will be displayed here in the viewport. So I will add one parameter to show you how to do this. In my R&D scene here, the whole site was full of parameters to keep track of all of them, but now we will just add one for demonstration purpose. Okay, so how to do it? On our camera here, let's do a left click on this little gear icon here and do an edit parameter interface. It takes a moment. It opens up, and there you have all the parameters you can add to your nodes. So what we are looking for is the comment parameter. So just put on the filter here comment. Let's switch to render properties and put the comment here again. And under viewport display category, OpenGL view, you will find the viewport command. Okay, let's move this over here, just drop it in the root of our camera, and let's change here from type string to a multi-line string to have a better overview. Okay, hit the accept button, and if you scroll down here on our camera, you will have the viewport command here. Let's test it. Test. Okay, and you will see now that here appears the word you put here. And for sure, it's also possible to link parameters. Let's do this with the particle separation. Right click here, copy parameter, move up again on our camera. Let's just drop it down, paste relative reference, and put here particle sep. Okay, that's fine. And it appears immediately up here. If you want to move it down, just put a few backspaces here. Okay, that's fine. Now if we do a flipbook, also in our flipbook we will have this parameter visible. So I think that's a really good way to keep track of all the changes and to be able to see what parameter you changed and what influence it had. So now let's take a look what parameters we need to change to get our flip simulation in the way we want. So the left part here is already fine, we tweaked it in the last clip. On the flip object itself, the only change we need to do before submitting it is to decrease the particle separation again to have more detail, and we shouldn't forget to disable the allow caching function to save some memory in the end. But for viewport previews, let's keep it activated. So most of the important parameters here are on the flip solver itself. The sub-steps are fine with the basic settings. On the particle motion we have to adjust a few things. So a collision detection is an important parameter. You have here two options, or basically three, but the first one is not interesting. So you have the particle collision detection and the move outside collision. So the particle one is the most accurate one. The move outside collision is a bit faster and it works also good with volumes. For us now to get the most accurate collision, let's keep it with particles. Let's take a look at the parameters down here. So behavior, reseeding, all this stuff here is fine for the moment. The separation we also don't need, but interesting now here are the droplets. Because we have really big waves and when they are smashing into our boat, it's likely that some flip particles will get a really high velocity impact and then they will fly away. So to be able later on to delete these particles, we want to detect the droplets. Droplets are basically the particles which are separated from the main fluid. I mean, there can be more than one particle, and exactly this threshold you will define here with the minimal and maximum particle density. So if it drops below the minimal particle density value, then it will be considered as a droplet. You have also some options with the behavior here. You could already kill them on detection, so they won't even fly in the air, but the standard value here is blend with fluid, so when they come back and drop onto our ocean, they will be just blended into the fluid, but they will have velocity impacts. It really depends on your needs. In some cases you are looking for this behavior, for example if you have a really calm lake where stone is dropping in and you have splashes and you want to have these splashes to have again an impact on your fluid surface, then it's fine, but in other cases you can just kill them on detection. We will keep these settings here, so we will detect them, then they will be put into a proper group, and in the end we can decide if we want to delete them or not. Okay, that's fine here. Vorticity and rest we don't need in our case. So the next step here is the volume motion. For the velocity transfer here you have two options, the splashy and the swirly kernel. The splashy one is recommended for oceans and the swirly is more recommended for stuff where you have high vorticities and you need to calm it down to have a nice surface. So in our case the splashy kernel is fine. The force scale is also fine. More interesting here for us is the collision tab, because here we can adjust the velocity and the velocity type of our boat. So I did several tests either with point and also with the other option, with the volume option here. I noticed that you get more dynamic and detailed splashes with the point option. With the velocity type volume the collisions were a bit more smoothed out. It also depends on what you are looking for, but as already mentioned when looking at the reference, most of the detail later on we will get from the whitewater. Because in the reference there was actually no water visible was splashing up, it was just the whitewater stuff. So that's why in the end I decided to use the volume velocity type, but if you have your own scenes, it's always good to do some flipbooks to see which velocity type is working best in your scene. Also keep in mind, if you have a deforming geometry which is changing its point count from frame to frame, you have to use the volume velocity, because it cannot calculate the point velocity properly because the point count is changing all the time. Okay, so in this case, volume velocity here, and we will increase our velocity scale so our splashes are a bit bigger here. Also an interesting parameter here is the surface extrapolation. As the default value, it helps the fluid to flow around curved surfaces properly, but with this value, or if you increase it even more, it can have a bit sticky behavior, so the fluid sticks on your collision and the splashes will be less dynamic. So I decreased it here to 0.25. Okay, as already mentioned, viscosity is not interesting for us, density divergence also not usable in our case, surface tension here the same thing, but on the solver tab we have to do some adjustments. Again, if you have a multi-core machine, it's recommended to disable the use preconditioner here to make full use of all your cores, so we will disable it, and that's it basically. Just to get a deeper understanding of all these parameters, I would recommend keeping this particle separation here for you, then varying these values, putting the values here in your camera, and just doing several flipbooks with a different velocity type, with a different velocity scale. You can on a particle motion, you can change the collision detection method. In the end, you will have a better understanding of all the effects of the different properties, and if you have your own flip scene later on, you can better decide which value have to be adjusted to get a desired look. But what I will do now here is to lower the particle separation to 0.06, make sure that we disable the allow caching here, and as already mentioned in the other scene, the best way here is to create a sim take. So just to create new take, include it here in the take, disable the allow caching function, and in the take list, it's already here, let's just rename it to sim. Okay, that's fine. And then on the output ROP, we just need to make sure to render the simulation with this take. Okay, that's fine. So get back up here. And to cache it out properly, we will go into the guided ocean layer fluid here in this node, and it starts calculating the actual meshed surface. I would recommend not caching directly out the surface, because the first thing is that it needs a lot of memory for the meshing process. And the second thing is that perhaps you will tweak the meshing settings of your fluid surface here later on, and it would be a waste of time to always resimulate the whole simulation if you just want to change the settings in your particle fluid surface node. So the best way is to use this node here to cache it out. These here are basically just our particles. There are some post-processing nodes which are fine. Interesting here is the fluid compress. It will pack our particles to save disk space, which is really handy and saves a lot of space. In earlier versions of Houdini, it was not unusual to have just the particles of your flip simulation had, I don't know, for 150 frames, 1 terabyte of cache data if it was a high-res sim. And now with this fluid compress node, which will compress it and also delete the bottom particles to just extend it later on in the particle fluid surface, so it really saves a lot of space. So let's adjust the path here as we always do and make sure it gets rendered with the take simulation. Let's say geo $hip name, that's fine. And again $hip name $os, that's fine. So now it will be written in a separate folder with $f for the current frame. Okay, one last check if everything is fine, but that looks good. And I would again recommend not just to save to disk, instead here to use the save to disk in background option, so the render scheduler will pop up like in the previous clips, and you can see exactly the progress of the simulation, but keep working in your current Houdini UI. And if you see that it's taking too much memory, for example, you don't have to close the main instance of Houdini, you can just kill the H batch, and it's better to judge the memory consumption because it starts from 0, and this Houdini instance here already used a lot of memory for all the stuff we were doing in this clip. One more thing we need to adjust before caching it out is to move our boat a bit down, because I noticed that in our boat sim the buoyancy was a bit too high. I mean, basically the motion of our boat is fine, but for our high-res flip sim it would be nice if our boat is a bit deeper below the water level. So let's drop down a transform sop here, put it here inside all streams, and just move it down by -0.5. It's not much, but it will improve the look. Before starting the simulation, you could also think about caching this collision source here out. That also depends on your memory of your machine, but sometimes it's also really useful to iterate. If you know that the collision settings are fine, you can just cache it out and then it will load much faster for the actual flip simulation. But for now we can just do it on the fly, so move back into your guided ocean layer fluid, make sure that you save your scene, then you can use the save to disk and background options to start the simulation. That's it for this clip and also this module. In the next one we will use the result of our high-res flip simulation to generate nice whitewater splashes. See you there.